March 3, 1943. RAF Burtonwood, England. A bitter wind howls across the airfield. Frost clings to the wings of bombers waiting in silence under a gray dawn. Their engines, the proud Merlins and Cyclones that power Britain's war in the sky, sit cold and stubborn. Inside the hangar, floodlights flicker over men in oil-stained overalls. Mechanics move with practiced desperation, their breath rising like smoke as they wrestle with lines of tubing and fuel couplings. Every few minutes, another engine coughs, sputters, then dies. The sound echoes off the steel walls, a hollow failure they've heard too many times. A corporal wipes his hands on a rag, blackened with oil. "That's the third one this week," he mutters. The officer beside him doesn't answer. His eyes are fixed on the temperature gauge still reading in the red. Across England, bomber crews wait for clearance to fly. But they can't. Too many aircraft are grounded. Too many engines have burst into flame on takeoff. The victims of a fault no one can solve. Engineers blame the cold. The cold blames the design. And in the middle of it all, one truth keeps returning in the maintenance logs: pipe fatigue, rupture at coupling, system failure. 5,000 aircraft rely on the same fragile veins of metal to carry oil and fuel at pressure through their hearts, and those veins are tearing themselves apart. The Air Ministry fears that if the failures continue, Britain's bombing campaign might collapse before it even reaches Berlin. But the solution isn't coming from a laboratory in Derby or a factory in Detroit. It's about to come from a plumber in Birmingham, and a pipe design so unconventional that the engineers will call it ridiculous. By the spring of 1943, the war in the air hung on a fragile edge. The Allied bombing campaign against Germany had begun to accelerate, the Royal Air Force pounding at night, the U.S. 8th Air Force striking by day. Factories in Manchester and Detroit worked around the clock to feed a sky that demanded more engines, more aircraft, more power. But inside those engines, the Rolls-Royce Merlin, the Wright Cyclone, the Pratt & Whitney Twin Wasp, a silent enemy was growing. It wasn't enemy flak, or sabotage, or faulty fuel. It was heat and metal fatigue. At 20,000 feet, the air was so cold that bare skin froze to steel. Oil thickened like tar. Metal contracted until joints strained. When the throttles opened and the engines roared into full power, everything expanded at once. Cylinders, pistons, and the miles of narrow tubing that carried fuel and oil through the machine. Every vibration from the propeller rippled through those lines like a hammer blow, and the pipes began to break. At first, it was written off as routine maintenance, a burst here, a leak there. But by March 1943, the pattern was undeniable. Engines were failing at an alarming rate. 1 out of every 10 bombers grounded for oil system failure meant a mission cancelled and a dozen men waiting helplessly on the runway. Every minute of flight demanded perfection. Every flaw cost lives. Logs from RAF Burtonwood told the same grim story. Oil line fracture at coupling. Engine fire. Aircraft lost. Mechanics patched one failure only to have another appear in the next sortie. Engineers thickened the pipes, welded new joints, and reinforced brackets, but nothing stopped the cracking. The cause was deceptively simple: rigid design. Each pipe, perfectly straight and tightly fixed, behaved like a prisoner under pressure. As the engine heated, the metal expanded, but with no room to move. It tore at its own welds. 1,000 tiny fractures waited for the next vibration to finish the job. No one could agree on how to fix it. Rolls-Royce wanted stronger alloys. Wright Aeronautical insisted on new fasteners. Bristol engineers proposed flexible rubber sections, but those froze solid in flight. Production chiefs warned that retooling would cost months the Allies didn't have. Meanwhile, the strategic picture was growing desperate. The Luftwaffe still controlled much of the continent. Every bomber lost on takeoff was one less aircraft over Essen or Hamburg. Commanders at High Wycombe calculated that if the mechanical attrition continued, bomber output might collapse entirely before summer. They called it the invisible offensive, an enemy inside their own machines. Factories filled with tension. Workers felt it too. The sense that their craft, however heroic, was betraying the men who flew it. Each burned-out engine brought backstories of crews bailing out over the channel, of planes never returning. It was around this time that a small subcontractor in Birmingham, assigned to produce cooling system assemblies for Merlin engines, received a new batch of orders. Among the fitters on that floor was a man whose name didn't appear on any engineering roster. Stanley Hooker, a plumber by trade, borrowed from civilian industry to meet wartime labor demand. His task was humble: inspect pipework, check for leaks, ensure each joint was clean before shipping. But what he saw disturbed him. The drawings demanded lines that ran rigid and straight from pump to manifold, locked in by clamps every few inches. Hooker had spent 2 decades installing pipes in basements and boiler rooms. He knew what happened when hot metal had no room to breathe. He'd seen it burst copper fittings in a city winter. To him, the problem wasn't the metal. It was the mindset. "You can't force pressure to behave," he would later tell a colleague. "You guide it." No one in that factory knew it yet, but that tradesman's intuition, born not in laboratories but in the crawl spaces of Birmingham, would soon give Allied aviation something it desperately needed: a pipe that could move without breaking. A design so simple it would sound absurd to trained engineers, a solution that would save more than 5,000 bomber engines before the war was done. The deeper the engineers looked, the worse the truth became. Inside every bomber engine, the ATO, problem repeated like a cruel riddle. Pipes that could withstand pressure, but not time. Every flight brought the same outcome: a hairline crack somewhere near a coupling, invisible to the naked eye until it became a jet of oil under 300 pounds of pressure. In seconds, that spray could ignite, turning a precision machine into a torch. By April 1943, the Air Ministry's reports read like obituaries. Loss attributed to oil line rupture, coolant circulation failure, fuel line fatigue. The RAF wasn't losing aircraft to enemy action. It was losing them to physics. The factories fought to keep up. In Castle Bromwich and Derby, production supervisors pushed new fixes: thicker welds, additional supports, new alloys hardened for stress. But each improvement only made the pipes more rigid and more prone to fracture. The harder they tried to fight the problem, the faster it came back. At Burtonwood, a weary maintenance officer summarized the madness: "We're designing machines of war that can't survive peace." By May, frustration had hardened into quiet despair. On the factory floor, Hooker kept watching the same errors being repeated, designs that looked elegant on paper but felt wrong in his hands. The lines were too short, the joints too tight, the curves too sharp. He ran his fingers along one finished section and said softly, almost to himself, "It's too perfect. Perfection breaks." Hooker wasn't an engineer in title, but he was a master of flow. Years in plumbing had taught him something most designers forgot: that pressure wasn't an enemy to be resisted, but a force to be accommodated. A system that could breathe under strain would outlast one that tried to stay still. He began sketching alternatives in the margins of test sheets. Small coils, gentle bends, loops that allowed expansion without tension. He'd seen the same principle used in industrial boilers, expansion loops that flexed under heat so the joints wouldn't fail. In aircraft, where every ounce mattered, such curves had always been dismissed as impractical. But to Hooker, they looked like the only thing that might work. When he shared the idea with a foreman, the response was predictable. "We're not building bathtubs, lad. We're building engines." The suggestion went no further. Still, Hooker kept thinking about it. If expansion couldn't be stopped, then it had to be managed, guided. He imagined a line that could flex slightly with vibration, like a living artery instead of a brittle tube. The timing couldn't have been worse for experimentation. Wartime production demanded speed, not curiosity. Every factory was already at its limit. Every engineer buried under deadlines. New ideas meant redesigns. Redesigns meant delays. So, when Hooker quietly built a test section using spare copper tubing and a makeshift coil, it was an act of quiet defiance. He mounted it to a test rig and watched as heat rose through the line. The pipe moved, just a fraction, absorbing expansion the way he'd hoped. When he cooled it again, it returned to shape without cracking. The welds held. He repeated the test with a standard rigid pipe. It fractured after 2 cycles. The results were undeniable. The ridiculous loop worked, but proving that to the establishment was another battle entirely. At the Air Ministry, engineers were locked in a debate over whether the solution lay in metallurgy or design philosophy. Hooker's loop didn't fit either argument. It wasn't stronger or more advanced. It was smarter. And in wartime Britain, with hierarchies as rigid as the pipes themselves, that kind of idea rarely survived first contact with authority. Yet change was coming. The data from field failures was becoming impossible to ignore. The ministry needed results, not reputation. And somewhere in the machinery of bureaucracy, Hooker's sketches, passed quietly from one sympathetic engineer to another, began to surface. By late summer 1943, an experimental team at Rolls-Royce received permission to run a live test on a modified oil system featuring Hooker's looped configuration. It would be crude, improvised, and unofficial. But if it worked, it could save thousands of engines, and perhaps the air campaign itself. The test would mark the beginning of an innovation so deceptively simple that the experts would call it foolish, right until the day it started saving their aircraft. In war, heroes often wear uniforms, but in 1943, one of Britain's quietest victories began with a man in work boots, not flying boots. Stanley Hooker's world was not the battlefield. It was the workshop. His war wasn't fought with rifles or Spitfires, but with wrenches and pipe cutters. He'd come from the same world as the men who built Britain's backbone: bricklayers, plumbers, metalworkers, practical minds who understood materials in their bones. He was born into trade, raised among tools that hissed, clanged, and steamed. To Hooker, a pipe wasn't just a conduit. It was a living thing. When water or oil surged through it, it flexed, vibrated, and sought escape. To control that flow was to understand nature itself. When the war began, Hooker's hands became part of Britain's industrial army. The government pulled thousands of tradesmen from civilian jobs into wartime factories. Their skill wasn't glamorous, but it was indispensable. While scientists wrote formulas, men like Hooker made them real. He arrived at a subcontractor's workshop in Birmingham in early 1943. Another face in the workforce, turning out cooling assemblies and fuel manifolds for Merlin engines. But to him, the work wasn't routine. Every unit he touched carried lives inside it. Each pipe he sealed was a lifeline for a crew that might never see home again. Hooker noticed things others ignored. He could feel vibration by touch, hear weakness in a fitting by sound. He didn't need instruments, he listened. When his foreman dismissed his concerns about rigid pipework, Hooker said nothing. He simply began experimenting after hours. He wasn't chasing glory or promotion. He just couldn't stand seeing waste, not of material, not of effort, not of life. If it breaks, we've built it wrong, he'd tell his mates. In those long nights, with rationed tea cooling beside him, he bent pipes by hand, shaping them into curves that defied the blueprints. To anyone else, it looked like nonsense. But to Hooker, it made sense in a way numbers never could. The war might have been global, but its salvation was taking shape in the quiet of a single man's intuition. To understand why Hooker's idea mattered, you must understand how close Allied aviation came to a mechanical collapse in 1943. Aircraft engines of the time were feats of brutal beauty. Powerful, temperamental, and unforgiving. A single Merlin engine contained over 30,000 parts, all moving under enormous stress. The system's lifeblood, oil and fuel, flowed through a network of pipes only millimeters thick. Those lines had to survive constant vibration, temperature swings from freezing to hundreds of degrees, and pressure surges with every throttle movement. The problem was movement. When metal heats, it expands. When it cools, it contracts. Each pipe could stretch and shrink several millimeters during a single flight. The rigid lines installed under the wings and around the engines weren't designed for that kind of motion. Over time, microscopic stress fractures appeared, invisible until they became catastrophic. Engineers called it fatigue failure. Hooker called it stupidity. He'd seen it before in plumbing, steam systems bursting because builders forced pipes into rigid alignment without giving them space to expand. The solution was centuries old, an expansion loop, a simple curve that let the pipe flex naturally, absorbing strain instead of resisting it. But in aviation, the concept was dismissed. Curves meant extra material. Extra material meant weight, and weight was the enemy. Aircraft design was a game of ounces. No one wanted to add an inch of tubing, let alone a loop. Hooker disagreed. Better a pound of pipe than a plane on fire, he told one engineer who laughed at his sketch. The beauty of his design wasn't just its function, it was its simplicity. The loop could be added without new alloys, new tools, or new machines. It was geometry, not technology. A single bend, carefully placed, allowed the pipe to expand, contract, and vibrate without stress. In field tests, the difference was astonishing. Standard rigid lines fractured after a few dozen cycles of heat and vibration. Hooker's curved prototype lasted hundreds. It flexed like a muscle, alive with motion. It wasn't elegant to look at, a small coil jutting from otherwise perfect machinery, but it worked. And in wartime, works was the only metric that mattered. In the summer of 1943, Britain's war industries were running out of patience and options. Engine failures were crippling sorties. Reports from Bomber Command described oil fires at altitude, system ruptures, catastrophic line failure. The Air Ministry's mechanical division demanded immediate solutions from its contractors. What arrived instead was ridicule. Hooker's sketches, for Tiohiu, Tsutiu, small loops in otherwise straight pipe diagrams, had reached the Rolls-Royce testing team. The engineers were unimpressed. "It's nonsense," one chief designer said. "It adds drag, weight, and manufacturing complexity for no proven benefit." Another scribbled plumber's fancy in the test notes. But one junior technician, exhausted after weeks of failures, convinced his supervisor to try it anyway. They built a single looped assembly and fitted it to a Merlin engine on the vibration rig. The test was supposed to prove Hooker wrong. After 20 hours of simulated flight vibration, the conventional straight pipe split along a weld seam. The looped pipe, Hooker's ridiculous idea held firm. The results were repeated, then documented. Heat cycles, pressure surges, vibration resonance. The loop survived them all. The data was clear, and it was impossible to ignore. Still, engineers hesitated. Adopting the design meant acknowledging that a man without formal training had solved what hundreds of them could not. Pride slowed progress faster than bureaucracy. But as failures mounted, pragmatism began to erode pride. The innovation spread quietly, first as field modifications, then as production adjustments. By late 1943, entire bomber squadrons were flying with the new flexible line assemblies. The difference was immediate: fewer leaks, smoother pressure readings, lower maintenance time. For a design so small, its effect was enormous. Hooker's loop didn't make engines stronger, it made them resilient. It turned rigidity into survival. He had reinvented not just a part, but a principle that strength in engineering is not resistance, but adaptation. Change in wartime rarely comes from the bottom. Factories were places of orders, not opinions. Hooker's design had to climb through layers of officers, engineers, and bureaucrats before anyone in power would listen. The turning point came at an inspection meeting in August 1943. Air Commodore Sir Harold Peake, who oversaw maintenance for Bomber Command, had grown furious with the endless reports of mechanical losses. "If this continues," he told his staff, "we'll be flying ghosts by winter." When a technician mentioned a plumber's new looped line that seemed to prevent failures, Peake demanded to see it himself. Within a week, he was standing inside the Rolls-Royce test shed, watching a running Merlin engine fitted with the new pipes. As the engine roared at full throttle, the gauges stayed steady. Oil pressure perfect. Temperature constant. No vibrations in the joints. Peake's reaction was immediate and unsentimental. "Standardize it," he said. "Effective immediately." That single sentence changed production policy across the country. Orders went out to retrofit existing aircraft and incorporate the loop into new builds. Factories that had laughed at the idea were now bending pipes by the thousand. Hooker received a quiet commendation, a note from the Air Ministry. Practical field innovation adopted for improved reliability. Well done, no ceremony, no medal. Just new orders, new tools, and 1,000 machines saved from failure. But in that silence lay the mark of true leadership, a recognition that good ideas care nothing for hierarchy. The war had forced men like Peake to realize that victory wasn't about rank. It was about listening to the people who understood the metal. Hooker's name never reached the newspapers, but his idea reached every corner of the Allied air fleet. While British and American bombers were becoming more reliable, the same could not be said for their enemies. The German Luftwaffe, once dominant in the skies, was beginning to crumble under strain, not only from Allied numbers but from its own mechanical limits. The Heinkel, a 177, Germany's long-range bomber, suffered catastrophic engine fires due to rigid fuel and oil lines that cracked under stress. Pilots nicknamed it Der Brenner, the burner. German engineers knew the problem but couldn't afford the time or materials to solve it. Their factories, battered by bombing, relied on rushed production and poor alloys. They tried to reinforce the pipes, to strengthen the welds, making the same mistake Hooker had watched his own factories make months earlier. In the end, the Luftwaffe's mechanical rigidity mirrored its strategic one. Every improvement came too late, every repair too rigid. Captured reports after the war would note that Allied bombers displayed remarkable fluid system resilience under sustained thermal stress. What they didn't realize was that the advantage came not from advanced metallurgy or expensive design, but from the humble flexibility of a single curve in a pipe. Hooker's principle, all études fitted en outvoer tant pis, that flexibility under stress meant survival. had become a metaphor for the war itself. By the end of 1943, Allied aircraft were flying farther, higher, and longer than ever before. Engine failures dropped dramatically. Crews began to trust their machines again. The skies over Europe, once ruled by fire and smoke, began to tilt in favor of those who had learned to bend before they broke. The innovation had passed its first trial. In design, in leadership, and in battle. But its true test, the moment it would prove itself beyond any doubt, would come soon, under the roar of hundreds of bombers heading toward a single, fateful invasion. The hangars no longer echo with hopelessness. Now they hum with anticipation. Rows of Lancasters and B-17s wait beneath the high trusses, their engines gleaming under inspection lamps. Each one carries a quiet secret inside its nacelles, a new curve of metal no longer straight but gently arched. Hooker's looped line had moved from experiment to practice. Thousands of engines had been fitted, tested, and cleared for flight. Yet no one knew how it would behave in combat, under the brutal rhythm of takeoff, climb, and fire. That morning, a formation of 300 bombers prepared for a strike against Augsburg. A proving ground for both the men and the machines. Mechanics checked fittings with gloved fingers, feeling the faint give of Hooker's coils beneath their touch. The loops looked awkward to the untrained eye, but the veterans knew better now. The old rigid pipes were death traps. These new ones flexed like tendons. At 600, engines roared to life across the airfield. White exhaust curled into the cold sky. Hooker stood beside the test officers as the first aircraft thundered down the runway. His stomach tightened with every vibration that reached his boots through the ground. He knew the mathematics of expansion, but he also knew war had a way of breaking mathematics. 10 minutes later, the formation vanished into the low clouds. The hangars fell silent again, leaving only the faint ticking of cooling metal. Hours passed. Mechanics waited for the sound they feared most. The distress call, the emergency landing, the fire truck bell. None came. At 14:30, the first bombers returned. Their engines were blackened by exhaust, but alive. Flight engineers clambered out with frozen hands and disbelief written across their faces. Pressure held steady the whole way. One crewman said, "No leaks." "Not one." Hooker said nothing. He simply nodded, wiping frost from his glasses. For months he had watched perfect machines destroy themselves. Now they were coming home whole. Over the next weeks, mission after mission confirmed it. Oil leaks dropped to near zero. Fire reports almost disappeared. Aircraft once grounded for endless maintenance were now flying 3-4 sorties a week. At the Air Ministry, engineers began charting the statistics. Between November 43 and March 44, engine-related aborts fell by over 60%. The numbers spoke louder than any commendation. The loop design was working, not theoretically, not experimentally, but in the unforgiving theater of war. Hooker became a minor legend among maintenance crews, though few knew his face. They called the modification the Birmingham Bend. Pilots joked that their engines had learned to breathe again. For Hooker, the success was vindication, not pride. He understood that he hadn't invented something new. He had simply reminded engineers of a truth as old as plumbing. Motion is inevitable. Design for it? Still, challenges remained. The invasion of Europe was approaching, and the coming months would demand an intensity of air power the world had never seen. Each mission meant hours of continuous engine strain. Each failure could cost the lives of 10 men and the success of an entire operation. The Air Ministry ordered a final endurance test, a continuous high-power run designed to simulate a round trip to Berlin. 2 Merlin engines fitted with Hooker's lines would run at combat output until either they failed or the fuel ran out. The test began at dawn. The roar was deafening. The vibration shook the steel-plated floor. Technicians monitored pressure and temperature readings, expecting gradual rise and eventual collapse. But the needles held steady. 1 hour, 2, 6. At 10 hours, the engines were still running flawlessly. When the fuel finally ran dry just after midnight, the lead engineer turned to the watching officers and said simply, "They've outlasted the clock." In the silence that followed, Hooker felt no triumph, only relief. For the first time since the war began, the machines would not betray the men who flew them. The following week, a memorandum was issued to all maintenance depots. Flexible looped oil and fuel lines to be standard across all bomber types. Immediate retrofitting authorized. By the spring of 1944, more than 5,000 engines carried Hooker's design into the skies. And on the horizon lay the operation that would decide the fate of Europe. An invasion that would test every system, every machine, every man. The world was preparing for D-Day, and somewhere in Birmingham, a plumber cleaned his hands, folded his overalls, and went back to work, unaware that his idea was about to carry an army across the sea. The night before D-Day. A low wind moved through the hangars, whistling between the rows of aircraft. Lancasters, Halifaxes, B-17s, Waimik, Afurt, Sint-Anton-Feet, lined like giants waiting to breathe. Inside the control sheds, mechanics checked and rechecked every system. Oil pressure, fuel flow, cooling circulation. Everything had to hold. This was the night no one could afford a failure. Hooker's looped pipes, now standard across Bomber Command, were everywhere, in the hearts of the Merlins and Cyclones that would thunder over the channel. Yet even he couldn't have imagined what would follow. At 23:45, the first bombers began to roll, 4 engines each, rising from the ground with a sound that shook the windows of the countryside. The air smelled of fuel and cold metal. Hundreds of aircraft lifted into the darkness, the beginning of the largest airborne operation in history. In previous winters, these engines might have faltered before clearing the coast. Rigid lines would freeze, crack, or leak as temperatures plummeted. But tonight, the gauges held steady. The engines ran clean and strong, their new pipework flexing with every surge and vibration. By dawn, as paratroopers descended over Normandy and the beaches erupted into chaos, Allied bombers filled the sky behind them, their engines a continuous thunder rolling over France. The mechanical plague that once grounded fleets had vanished. At Burtonwood, Hooker followed the mission reports as they came in through the crackling teleprinter. Not a single aircraft had been lost to engine fire or line failure. Not one. For a man who had spent months listening to engines die, that silence, the absence of bad news, was deafening. Days later, as the invasion expanded inland, the reports kept coming. Lancaster squadrons flew record numbers of sorties. B-24s returned with bullet-riddled wings, but their engines still running. Mechanics began calling the new systems breathers. They joked that the machines finally wanted to live. For the Air Ministry, the statistics were staggering. From January to June 1944, engine-related mission aborts dropped by nearly 70%. Fire reports were virtually non-existent. Across the continent, bomber reliability became the unspoken edge of the Allied campaign. It wasn't glamorous. No headlines, no parades, but it was decisive. Because every time a bomber returned, it carried 10 men who might otherwise have been lost to heat, pressure, and broken metal. Every time an engine kept running, a mission completed, a bridge destroyed, a convoy halted. Behind every successful strike lay a curve of pipe. A plumber's sketch made real. Hooker himself never left England. He wasn't in Normandy or over Berlin or flying escort in the cold blue skies. He stayed in Birmingham, overseeing manufacturing adjustments and training new fitters. To his co-workers, he was the same quiet man with the same tea-stained notebook. But when the invasion succeeded and the Allies secured their foothold in Europe, the ministry sent him a brief telegram. "Your pipe design has performed flawlessly under combat operations. On behalf of the Air Ministry, thank you." He folded it carefully and put it in his pocket. That was enough. For historians, the success of Operation Overlord was a symphony of strategy, courage, and technology. Radar, deception, logistics. Yet beneath it all were the small miracles. The weld that didn't fail, the pipe that didn't crack, the mechanic who refused to give up. Hooker's loop wasn't just an engineering fix. It was a philosophy made metal, that endurance depends not on rigidity, but on the capacity to flex. As the summer of 1944 turned to autumn, Allied aircraft filled the skies from Normandy to the Rhine. The mechanical crisis of the previous year was forgotten, swallowed by victory. But somewhere, amid the roar of engines and the hum of the factories, the echo of that forgotten moment remained when one man's understanding of pressure and patience had turned the tide of machinery, and with it, the war. For every bomber that reached its target that summer, for every crew that came home, a small loop of pipe had bent just enough to save them. And though no one would ever see it, no metal could have shone brighter than the dull, oil-stained steel that kept them alive. By the autumn of 1944, the skies over Europe told a different story. The endless smoke trails that once marked engines burning out over the Channel had vanished. The Allied air fleet, once plagued by mechanical fragility, had become a machine of staggering reliability. At bases from East Anglia to northern France, maintenance crews finally found something unfamiliar: rest. The constant churn of emergency engine replacements had slowed to a rhythm of routine service. Mechanics who once worked through the night now watched bombers land with all 4 engines still running, their nacelles free of fire and oil mist. The data from the Air Ministry confirmed what the crews already knew. In the 6 months following D-Day, engine-related mission aborts fell by more than 2/3. Fuel line ruptures, once a daily occurrence, were nearly eliminated. Field reports spoke of oil systems performing beyond expectation. Hooker's looped pipe design had quietly rewritten the standard for endurance. By September, over 5,000 bomber engines had been retrofitted with flexible line assemblies. The modification was simple enough to implement on-site: a handful of new bends, 2 brackets, a replacement coupling. But its effect rippled across the war effort. Each saved engine meant one more bomber in the air, one more target reached, one more step toward victory. It wasn't just about machines, it was about time. Before the innovation, maintenance crews spent hours rebuilding systems after every sortie. With the new design, engines ran for weeks without major repair. The manpower saved could be redirected to other tasks: navigation upgrades, radar calibrations, structural repairs. The entire operational tempo of Bomber Command accelerated. Factories noticed it too. Rolls-Royce engineers at Derby began integrating Hooker's loops directly into their Merlin production lines. In the United States, Wright Aeronautical quietly adopted the same principle for the massive Wright Cyclone engines that powered B-17s and B-24s. The looped line, once ridiculed as unprofessional plumbing, had become doctrine. Official reports from the ministry's engineering branch were restrained in language, but monumental in meaning. Implementation of flexible, looped fluid lines across high-output engines has contributed substantially to sustained reliability under combat conditions. Estimated preservation exceeds 5,000 engine units. Those words, "preservation exceeds 5,000, were the measure of a war won not only in strategy, but in craftsmanship. Hooker, still in Birmingham, never saw himself as a hero. His name appeared on no official citation, no broadcast, no medal list. When asked about it later, he would shrug. The lads flew home. That's what matters. His pride was practical, not personal. Each bomber that returned intact meant the idea had done its job. By year's end, even the Americans had taken notice. The 8th Air Force maintenance reports listed the flexible design among critical field modifications contributing to sustained operational readiness. Hooker's innovation had become invisible, absorbed into standard procedure, its origin forgotten in the constant forward march of production. Yet in those cold, oil-slicked hangars where the war's machinery lived and breathed, his idea had changed everything. The smell of burnt oil that once hung heavy over every shift had thinned. The crews no longer cursed the engines they served. There was a sense, faint but certain, that the machines had finally begun to work with them, not against them. It was a small victory in the great storm of war, a quiet, mechanical miracle that made thousands of louder ones possible. And as 1944 turned to 1945, the war in Europe neared its end. The bombers still flew, the engines still thundered, and inside each one, Hooker's loops flexed and breathed, silent, unseen, and indispensable. When the war ended in 1945, the engines fell silent. Across England, hangars that once roared with life stood still, tools neatly stacked, the smell of oil replaced by dust. The great machines of war, those restless iron lungs, were finally at peace. For the Air Ministry, the end of fighting brought paperwork. Reports, analyses, audits. The accounting of a victory measured not only in missions flown, but in engines saved. Somewhere among the thousands of pages filed that summer, buried between test summaries and manufacturing orders, was a single sentence. Field adaptation of flexible looped line assemblies has contributed materially to improved engine survivability. No name attached, no signature, just a line of acknowledgement in the vast machinery of bureaucracy. Stan Hooker returned to Birmingham a few months later. The war factories were winding down, and men like him, temporary wartime specialists, were quietly released back into civilian life. He went home to the same streets, the same brick houses, the same smell of coal smoke in the morning. The world had changed, but his life had not. He reopened his small plumbing business. The same skills that had once saved engines were again used to fix leaking radiators and kitchen boilers. When asked about the war, he spoke little. "I worked on engines," he'd say. Nothing more. The people who knew him never suspected that his idea had rippled through air bases across Britain, or that it had saved thousands of lives. To them, he was just Stan, dependable, quiet, good with his hands. In the years that followed, his design spread beyond the war it was born in. Jet engines replaced pistons, but the principle remained. Expansion loops and flexible couplings became standard practice in aviation fluid systems. The same geometry that had saved Merlins now lived inside turbines, cooling lines, and hydraulic systems. Engineers gave it new names. Expansion compliance, flex tolerance, dynamic line compensation. The terminology changed, but the heart of it never did. Hooker's loop became invisible by design, absorbed into the very language of modern engineering. In the 1950s, as Britain entered the jet age, Rolls-Royce technicians incorporated refined versions of his layout into the Avon and Conway engines. The same logic spread to American designs. Pratt and Whitney, General Electric, and eventually into commercial aviation, where every long-haul jet flying today carries some descendant of that wartime curve. Hooker lived long enough to see those early jets streak across the sky. He'd look up sometimes from his workshop doorway, pipe wrench in hand, and smile faintly. He never claimed them as his legacy. Perhaps he didn't need to. In 1968, a retired engineer who had once served under Air Commodore Peake published a memoir about wartime innovations. In a footnote, he mentioned a plumber from Birmingham whose understanding of pressure and flow saved countless engines. No name, no citation, just that phrase. That was enough. Hooker passed away quietly in the late 1970s. His obituary, like his life, was modest. Stanley Hooker, plumber and wartime fitter. There was no mention of his contribution to aviation, no recognition of the thousands of men who had lived because of it. But among those who had worked the hangars of Burtonwood and Castle Bromwich, his story lingered. Untrained, told over tea breaks and among veterans' reunions. A few remembered the first time they saw those strange curved pipes, the ones that looked wrong until they realized they never failed. To them, Hooker wasn't a hero. He was something rarer, a man who did what needed to be done, perfectly, quietly, and without ever asking to be remembered. The war had ended. The machines had survived. And somewhere in the structure of every modern aircraft, hidden in the veins that carry oil and fuel, his idea still lived, humming softly, flexing with every heartbeat of flight. History often celebrates the men who commanded armies or built empires. But the truth is, wars and the peace that follows are shaped just as much by those who built things that worked. Stanley Hooker was one of them, a man of tools, not titles. He never gave a speech, never wrote a manifesto, never claimed genius. He simply saw what others couldn't, that perfection in metal is not found in rigidity, but in its ability to move. His idea didn't roar or explode. It didn't draw applause. It flexed quietly, unseen, holding back pressure so that thousands of engines could keep breathing. And in that silent resilience lay the very principle that defined the war's outcome. Endurance. Hooker's loop wasn't just a mechanical fix. It was a metaphor for survival itself. The Allies won not because they were unbreakable, but because they learned how to bend without breaking way, in factories, in aircraft, in the hearts of the people who refused to give up. Every war teaches something to those who build it. This one taught engineers humility. It taught commanders that brilliance can come from a workshop floor. And it reminded the world that simplicity, when born from understanding, can be the most powerful form of sophistication. Today, every aircraft, from fighter jet to passenger liner, carries echoes of Hooker's lesson. The curve of a pipe, the give in a bracket, the tolerance in a seal. Each is a whisper from that frozen hangar in 1943, when one plumber refused to believe that a straight line was the only way forward. He never sought fame, and history almost forgot his name. But every time an engine starts and stays alive through heat, motion, and time, his legacy endures quietly, faithfully, like the flecks of his loop beneath the metal skin of flight. Because in the end, the greatest strength in any design or in any life isn't the ability to resist pressure, it's the wisdom to yield to it and still hold strong.